Hi, I am Anand Patel, a field applications engineer from the Cloud Power Group at STMicroelectronics. Today, we are going to talk about STBuck, a multi-phase buck converter based on ST's patented stacked buck architecture. STBuck is based on a non-isolated multi-phase buck converter topology which provides regulated output. Now, let's look at the concept diagram of the STBuck. As you can see that STBuck is constituted by two buck phases, mainly stacked phase and buck phase. These two phases are serialized at the input and parallelized at the output. Serialization at the input allows the drain to source max voltage swing of the MOSFET to be Vin by 2, thus allowing the use of low voltage MOSFETs. On the other hand, parallelization at the output allows us to share the total output current between two phases, thus reducing the conduction losses. No current sharing circuit is required between stacked and buck phases. We are using PM6779 as our controller for the STBuck. PM6779 is a digital controller which works on the innovative STVcot control architecture, which combines the advantage of both voltage mode and constant on-time control techniques. User can configure the controller through GUI using PMBus interface. To drive the MOSFETs, we have used ST's STPRD-C02A, a high voltage full bridge gate driver. The driver is configurable and optimizes the driving scheme for the STBuck to improve power density. In this demo, I am going to cover our evaluation board of single cell STBuck with the coupled inductors. Use of coupled inductor allows us to have reduced phase ripple current for the same value of inductance, thus improving overall efficiency and power density. The board used in this video can support up to 850 watt of thermal design power. Here to show the improvement in power density, we have put our previous version of STBuck board with non-coupled inductor in parallel to the board with the coupled inductor. You can clearly see the size difference. Next, we will quickly see the evaluation board used in this video. There are 6 MOSFETs forming the buck and stacked phases. The controller PM6779 is on the left, and in upper center part of the board there is a coupled inductor. The actual solution board area is 85 mm x 35 mm. Now let's look at our first experiment's waveform. In this experiment, we are going to provide 54 volt as input and analyze the phase node voltages. Output of the converter is set at 12 volt. An oscilloscope is connected at switching nodes of two phases of the STBuck board. As you can clearly see, for the input voltage of 54 volt, the phase node voltage is around 27 volt. Thus, we can use lower VDS rated MOSFETs with lower RDS on, which turns in lower conduction losses and lower switching losses since the switch node voltage is half. We can also see that the duty cycle of the phase node voltages is near 50%, which provides almost equal utilization of upper side and lower side MOSFETs of a same phase, as well as it provides good controllability. For the second part of the demo, we are going to show the load transient capability of the STBuck. We have slightly modified the setup from the previous experiment. An E-load is connected with the board. A current probe is used to measure the output current and a voltage probe is connected to see the output voltage. We are here applying a transient step load of 5 ampere to 25 ampere with a slew rate of 2.5 ampere per microsecond. From the output voltage waveform, you can clearly see that our board with the coupled inductor is able to handle the load transients quite well. Another advantage of STBuck's architecture is its scalability. More cells can be connected in parallel in order to achieve higher power solutions. In this evaluation board, 4 STBuck cells are connected in parallel and operated by a single PM6779 controller. Thermal design power of this evaluation board is 3.2 kW. In summary, I can say that STBuck is a highly efficient and scalable multi-phase buck converter topology. With the use of coupled inductor, we can further increase its power density and efficiency. Thank you for watching this.